All right, Rich, you want to start?
All right.
Remember, I don't think they may not have learned it yet, but we'll start from the beginning. Yeah, so I don't know how many of y'all went over Lewis structures yet, but we're gonna start from the beginning and kind of tell you how to determine the amount of bonds, the amount of lone pairs, what a Lewis structure is, all that stuff. So
Yeah, we'll basically start from the ground up. So we're gonna ignore all this stuff for now, like all the stuff that I'm underlining in black. We all don't have to do that right now. That'll be for a later date. So once you are more comfortable with Lewis structures, stuff like that, we can go into the more difficult stuff, which is that stuff. But for now, let's just get into practice, get in the habit of drawing Lewis structures. So let's go through first and make a list of steps. So step one, what you're going to do is determine total valence electrons. Like, for example, let's determine the valence electrons in this compound, CH4. So how many valence electrons does carbon have? Anybody is free to answer.
four, Sydney said.
4 valence electrons for carbon, right?
No, Daniel, there's not a PDF, but we can send this out after the session, so y'all can work on the rest. Okay.
All right, and then how many valence electrons does hydrogen? 1. So, and there's 4 hydrogens, so 4 plus 4, there's 8 total valence electrons.
And before we move on, I guess, because maybe some people don't know how to determine how many valence electrons, how would you determine it, Rich, if you didn't know off the top of your head?
So if I did not have any prior information on how to determine valence electrons, I can use my good old friend, the periodic table. So as you can see, carbon is in group 4, meaning that it has 4 valence electrons. That's how many electrons are there in its outermost shell. Now that's for carbon. Hydrogen, as you can see, is in group 1. And group 1 elements only have 1 valence electron. So if carbon has 4, and then there's 4 hydrogens, 4 plus 4, that's 8 valence electrons. Now, step number 2 is identify central atom and draw bonds to surrounding atoms. Now, you might be wondering, how do you determine which one is the central atom? Normally, I'll write this up here. So central atoms often have low electronegativity, or they're the smallest number there. What I mean by smallest number is, if we look at CH4, the thing is with carbon, there's only 1 of them, so we can assume that carbon, in this case, is our central atom. And then carbon normally has a lower electronegativity as well, so we can, And then, so we identify our central atom, which in this case is carbon. So we'll go ahead and draw carbon right here. And then we'll draw our surrounding hydrogen atoms around it. So like this. 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, and 1 hydrogen right here. So then we identify our central atom and now we need to draw bonds to our surrounding atom. What do I mean? You just connect the carbon and hydrogen with a line like that. So let's go ahead and do that for the remaining 3. Like that. Now, how many electrons are in a bond? Anybody? How many electrons are? Yeah, 2 electrons. 2 electrons are in a bond. Thank you, Sydney. So 2 electrons in a bond. So what you have to do is, since we made 4 bonds, how many electrons did we use up? If there's 2 bonds per electron and we made 4 bonds, 8. And if you remember, 8 is the total amount of electrons you have. So you subtract by 8 and you get 0 valence electrons left over. Congratulations, you all just drawn your first Lewis structure ever. Probably not ever. For some of you. For others, y'all are pros in the Lewis structure game. But here's how you draw out a Lewis structure. Now, let's go through the steps for something. Say we have more leftover electrons. If you have more leftover electrons, what you're going to do is draw remaining electrons as lone pairs. What the heck does a lone pair mean? It's well, I'll show you in the next. Oh, sorry. Central atom is one with more electronegativity, not least. Oh, wait. Yeah, more electronegativity. All right. So let's do this next one. NCl3. What's our total number of valence electrons? How many total valence electrons do we have? $26 total valence electrons. Because again, nitrogen is in group 5, so it has 5 valence electrons. Chlorine is in group 7, so it has 7 valence electrons. 7 times 3 is 21, plus 5 is 26 total valence electrons. So next, we'll identify our central atom and draw bonds to our surrounding atom. So in NCl3, the nitrogen is going to be our central atom. The most electronegative, and there's only one of them there. So NCl, and then we're going to draw a bond to the surrounding atom. So here, here, and here. So if we drew 3 bonds, how many electrons did we use up? 6. So 26 minus 6, there's 20 electrons left over. Now, what you're going to do is draw the remaining electrons as lone pairs on the surrounding atoms. So, what do I mean by that? So you go like this. You're going to go, just draw 2 dots right here. These 2 dots is what's called a lone pair. Some of you over at Health Careers have been exposed to the line method where you draw it like that. I do not like that method. And let me tell you why. In OChem, when you draw like your new structures and stuff like that, they expect you to draw your arrows, your curved arrows from your lone pairs. And so they need to clearly see that, like, that's 2 dots right there and not a line.
Extremely important.
Yeah.
I did not take Health Careers, so I have no saves.
Good, nice.
So now you can draw your lone pairs.
HCl.
So 2 dots right here. Now, a thing to note is the reason why I'm drawing 6 lone pairs around my chlorines is because of something known as the octet. So it says that an element cannot have more than 8 electrons. Or you'll learn that there are some exceptions to that rule, but in general, for anything like if you look at the periodic table in the 2nd period and above, so anything like generally before like phosphorus, that's where you'll have an octet. So these elements cannot cross 8 electrons at all.
And terminal atoms typically only max out at 8 electrons, whereas central atoms can expand their octet, and we'll see some examples later. Actually, maybe we can do one in just a little bit. You'll see that, hey, this is exceeding the octet rule by a lot, but that's okay for that element specifically.
Yeah, but in this case, y'all won't have to worry about that. So an element cannot have more than 8 electrons. That's why if you look at the fluorine right here, there's 1, 2, 3, 4, 5, 6, and the bond is 2 electrons. So the chlorines are happy with 8 electrons. And then that goes for any chlorine atom. So all of it has 8 electrons surrounding it. So 20 minus 18, we're left with 2 electrons. Now the question is, where do we put these 2 electrons? If we have to follow the octet rule, which atom would we place them on? On the nitrogen. Good job, Sydney. On the nitrogen. So we draw out a lone pair right here, and minus 2. So basically, we keep going until we're left with 0 electrons. And then the last and final step is if or you keep going until there are 0 electrons left. And if you go negative, which does happen, draw double / triple bonds between atoms. So just to sort of recap our steps. So step 1, we determine our total number of valence electrons. In this case, chlorine had 7, nitrogen had 5. So 7 times 3 is 21, plus 5 is 26. The 26 total valence electrons. We identified our central atom, which we determined to be nitrogen, because it has a high electronegativity, and there's only one of them. And we drew our bonds to our surrounding atoms. So because we drew those bonds, 26 minus 6, we have 20 electrons remaining. So we drew out those 20 electrons as lone pairs on surrounding atoms, or I should also add / central atom. So we drew the remaining electrons as lone pairs on surrounding atoms and central atoms. So in this case, we have 6 electrons here for our chlorines. So we drew our 3 lone pairs, so it's 18 electrons we used up, because there was 3 lone pairs we drew on the chlorines each, which is 6 electrons total. So 6 times 3 is 18. So there's 2 electrons left. Now those 2 electrons we did as lone pairs on the central atom. So 2 minus 2 was 0. And we didn't need to do step 4 in this case because we got to 0 electrons and we didn't go negative. And we shall see certain examples later in
I can,
this worksheet where you can go negative.
I can take it or not, right, we can switch off. That's cool. All right. I'll do 3, wait, how many? I'll do 2 and then you'll do 2. Okay. All right, so now you're stuck with me for the next 2 questions. So Rich did a great job at giving you an introduction into Lewis structures. So let's continue with where he left off. So I want to jump down to E, all right? So first, let's identify how many valence electrons first, because that's what Rish said is our first step. So determine the total number of valence electrons, and how many does carbon have? Carbon. 4. Thank you, Sydney. So we have 4 for carbon. And then hydrogen, we said has 1 valence electron, but we have 2 hydrogens, which means that each one contributes 1 valence electron. So we have a total of 2 valence electrons coming from the hydrogen. So we have +2. And then how many valence electrons does oxygen have? 6, right? It's in group 6 of the periodic table, the main group. So it contributes 6 valence electrons. So we have a total of 12 valence electrons. So valence. So now what we typically will do is figure out which one the central atom is. And for most cases, when you have carbon in a formula, carbon is going to be your central atom because carbon loves sharing its electrons. And it's the reason that there's an entire year worth of chemistry called organic chemistry specifically made for carbon-based compounds because carbon is so unique in that it loves sharing its electrons. So carbon is the central atom. And typically, I think Rish said that it has more electronegativity, but it would make sense that if the central atom had the least amount of electronegativity, because it's more willing to share its electrons than want to take on electrons. So and I know you may not know what electronegativity is yet, but we'll get to that in a little bit. But the central atom will typically have the least electronegativity because it wants to share its electrons among all the other terminal atoms.
So we're at the first step. Moral of the story, don't second guess.
Exactly. Rish was right, but like on the test, you don't want to second guess yourself. Trust your gut. Anyways, so we have technically the one with the lowest electronegativity is hydrogen. However, hydrogen can only form a single bond. Therefore, you're never going to see hydrogen as a central atom because it can only form one bond, so that would be the worst central atom possible. So central atoms are things that like to form multiple bonds, such as carbon, and they like to share their electrons because they're low they have a low electronegativity relative to the other atom. So we draw our carbon, and we draw our elements surrounding it. So we have two hydrogen, H here, H here, and then we have an oxygen. So the next thing we would do is draw a single bond to each other terminal atom. So from our central carbon atom to hydrogen twice, and then one from our central atom to our oxygen. So at this point, we would do a tally up how many electrons we've used so far. So how many have we used thus far? 6, right? Because there's two in each bond. So we have 3 bonds we formed. So that's 2 times 3 is 6. So we have 12 valence electrons minus 6 valence electrons, or 6 electrons that we just did or used up. So now we have 6 valence electrons left over that we need to put into the structure. So at this point, I would figure out how many more electrons we need to satisfy this structure using lone pairs. So if we do that, we see that we need how many more electrons does oxygen need in this structure? So Susanna says 2, and there's a specific rule that Rish mentioned earlier. It's the octet rule that says elements in period 2 and some other elements like chlorine and things, they like to have 8 outer electrons, and that's called the octet rule. So right now, oxygen only has 2 valence electrons because it's sharing the 2 with carbon. So if it wants to get 8, you would need 6 more. So we put those on as lone pairs. So someone said 6, and that's the right answer. So we would put them on as lone pairs. So 1, 2, 3, 4, 5, 6. Therefore, oxygen would need 6 lone pairs, or 3 lone pairs for a total of 6 electrons. And how many more lone pairs would carbon need to satisfy its octet rule? If it has, well, first we need to see how many it has. Right now it's sharing 2 here, it's sharing 2 here, and it's sharing 2 here. So it has a total of 6, 2, 4, 6. So it needs how many more? Could you add a double bond to the C and O? You could, but we're not there yet. And wait, can you explain why specifically oxygen and not hydrogen?
Hydrogen is what we call one of the exceptions to the octet rule, so it's only satisfied with 2 electrons, so it's just happy with its bond right there. That's why we go with the oxygen, which needs that 8 electrons. If we put more electrons on the hydrogen, then it's not happy anymore.
Yeah, and if you remember from chapter 7, we learned about all the orbitals and quantum theory, and hydrogen is in the 1s subshell. And we know from our quantum numbers that our first energy level only has an S subshell. So N equals 1, L can only equal 0, and then M sub L equals 0, and then M sub S can be whatever. Because atoms want to fulfill their outermost energy level, since hydrogen's outermost energy level is the first energy level, and the first energy level only contains an S subshell, meaning it can only fit 2 electrons in it. So if you try to add any more to that, you're going to exceed the amount that that subshell can hold, which is why hydrogen can only take on a total of 2 electrons. And that's why it's satisfied with this bond alone, and you don't need to add lone pairs to it. Does that make sense, Susanna? If it doesn't, okay, perfect. If it doesn't, if you need a better explanation from Rish, let me know, because sometimes my explanations can be bad. Anyways, how many lone pairs should we put on carbon for it to fulfill its octet? 2, right? Thank you, Sydney. So we're going to put 2 there. So now what we want to do is figure out how many electrons we used up in red. So because we already subtracted the bonding electrons. So we had 6 left, but we put 2 here, 2 there, 2 there. So that's 6 that we put on oxygen. And then we put 2 more on carbon. So that's 8. So when you do your subtraction, you get -8 valence electrons. It gives you -2 electrons. So you're actually deficient in electrons, which is when we go to Rish's rule number 4, which we're gonna eventually put these onto some constitution called Rish's rules. And Rish's rule number 4 says if you go negative, draw a double bond or triple bonds between your atoms. So whenever you go negative, it means that you have some amount of degrees of unsaturation. And what that means is that you just have a double bond somewhere in your molecule. Just like maybe you've heard of saturated and unsaturated fatty acids in biology. Unsaturated fatty acids have double bonds. In this case, the -2 indicates that this compound is not completely saturated. So it's unsaturated, meaning you need to put a double bond. And I'm going to ask y'all, where should we put the double bond? There's 3 places we can put it, right? We can put it between this carbon and hydrogen, or between this carbon and hydrogen, or between this carbon and oxygen. Where would we put it and why? In oxygen. Kennedy says oxygen. Daniel says C, carbon equals oxygen, whatever that means. Yeah, I know, I was just messing. Yeah, so y'all are right. It would be between carbon and oxygen, because we had said, we know and we understand from chapter 7 that hydrogen can only have 2 electrons in its outermost shell. So you can't form a double bond between carbon and hydrogen, because if you did, that means hydrogen now has 4 electrons, and we know that's not going to happen, at least in this universe. So we put it between carbon and oxygen. So now we start from the top again. I would normally just rate that and say, okay, so we have 2, 4, 6, 8. We used up 8 in our bonding electrons. So subtract, so we have 4 left over. And how many of these atoms need lone pairs to fulfill their octet? And which one? Oxygen, right? Because now oxygen has only 4 electrons because it's sharing 4 with carbon. Carbon is good though, because it has 1, 2, 3, 4 bonds. 4 bonds means it has 8 electrons, and that fulfills the octet rule. So these electrons that are left over clearly need to go onto the oxygen for it to fulfill its octet, and they go on there as lone pairs. And like Rish said, we don't do lines like this if you came from health careers. No shade, we love our friends from health careers, but for chemistry purposes, it's always dots, never lines. Isn't that right, Taylor? Taylor was not, she was not one of the 4 souls that were taken by them. Exactly. Okay. Does that make sense for everyone? Yes. Or no? Or maybe so. Are we good? Sydney, Kennedy, thank you, Ariana. Awesome, perfect. Okay, so let's go ahead and go on to F. First thing we do, Rish's rule number 1 is what? What do we do first? We're doing number or letter F now. Valence. What about the valence, Daniel? Find them. They're probably on the atoms. What do you mean by find them? You mean like add them up and count them and get the total number of valence electrons? Okay, I think that's what you mean, Daniel. Perfect. So carbon, we already had dealt with carbon a couple times. We know it has 4. And we know hydrogen brings 1 electron to the table, so 4 plus 1. And then we had mentioned in the example Rich did earlier with nitrogen, that nitrogen brings how many electrons to the table? Valence electron. 1. So Sydney says 1. That would mean nitrogen is a group 1 element, but it's not. Hydrogen, or I think Sydney might have been talking about hydrogen, but we're talking about nitrogen. Yeah, exactly. See, I know Sydney got her money up. So anyways, I think Daniel said that it brings 5 electrons to the table because it's in the 5th main group. So plus 5. That gives us 10 valence electrons. What's the next thing we do? Find central atom. Perfect, Susanna. Skeletal structure. Yeah, so we're gonna go ahead and figure out which one this central atom is and put the surrounding terminal atoms around the central atom. So in this case, what do you think the central atom is? I got a feeling it's carbon, right? Because carbon is fairly good at sharing its electrons, right? So let's go ahead and put carbon in the middle, like y'all said. And we put our nitrogen and our hydrogen on opposite sides. So the next thing we do is draw a bond from the central atom to the terminal atoms. So carbon to nitrogen, carbon to hydrogen. And now we figure out how many electrons we've used up so far. So we started with 10 valence electrons. We used up so far we've used up 2 in this bond and 2 in this bond. So we've used up a total of 4 valence electrons. So 4 electrons here. This gives us 6 more electrons to work with. Now, how many electrons in terms of lone pairs are needed to satisfy this molecule now? So just 4. Let's see. We know carbon, things like carbon and nitrogen like to fulfill their octet. Right now, carbon has 2 bonds, meaning it has 4 electrons, so it needs 4 more. So we're going to put those 4 more in purple. And then nitrogen likes to fulfill its octet as well. So but it only has 2 electrons, right, in that one bond. So we're going to need to add up to 8. So 1, 2, 3, 4, 5, 6, and then it has the 8, the other 2 from this bond. So now it has a full valence electron, full shell. So in order to make this happen, we needed to add how many electrons? Yeah, 10, right? We added 6 on nitrogen to fulfill its octet, and 2 lone pairs on carbon, so 4. So a total of 6 plus 4 was required to fulfill all the octets of the atoms. Now, what we do is say, okay, let's do 6 minus 10, and this is already a red flag. You're doing 6 minus 10, right? So we get negative 4 electrons. So we're deficient 4 electrons, and if you're deficient 4 electrons, that means you need to either add 2 double bonds somewhere or a triple bond somewhere. In this case, what if I wanted to do this? What if I was like, you know what? It's exam day. I forgot to read the chapter. I know I need to add some double bonds, so I'm just gonna do that. Is that perfect? I mean, everything's got a full octet, right? No, yeah, Sydney's like, that's wrong. So what I did wrong was added a bond to hydrogen, another bond to hydrogen, which expands its octet, or not octet. It expands its rule of 2 electrons. That's not what we want to do. So what we would want to do is instead go ahead and just put a triple bond between where? Obviously, there's only one other place, Dylan, right? So carbon and nitrogen. So we put 2 more bonds there to form a triple bond. Does that satisfy carbon's octet? Yeah, right, because carbon has 4 bonds now, meaning it has a total of 8 electrons, so it's all good for carbon. So let's see how many electrons we use up. We use 2, 4, 6, 8. So 8 minus, or 10 minus 8 gives us 2 electrons left over. And we know that we still have nitrogen doesn't have a complete octet, right? Because it only has 2, 4, 6 electrons in those bonds. And it needs a lone pair in order for it to have a full octet. Therefore, we would put these last 2 electrons onto that nitrogen atom, and we would do minus 2 electrons. So we're left over with 0 after that. So that's a perfect Lewis structure. That's 100 on an exam right there, if that was the only question on the exam. Are there any questions before I toss it back over to Rish? How do you feel about doing something like this, Rish?
Oh, one of those.
Okay. Maybe we can toss them with something different. And yes, before y'all might see this on your take-home assignment maybe eventually, but xenon on the periodic table, xenon's classified as a what? Xe is xenon. Xe, xenon is classified in a group of elements that are very special because they are noble gases, right, Daniel? Exactly. And noble gases are known to not want to form bonds, but it's weird because we actually do see xenon tetrafluoride, and it exists. So xenon and krypton are among some of the only, I think they're the only noble gases that are able to form bonds. It gets weird once you start talking about that stuff, but just know that it can happen. So maybe if we'll give Rich a shot to walk y'all through that one.
All right, xenon tetrafluoride. A lot of you might be intimidated because you saw the xenon right here, but have no fear. It's the same set of rules as before. So according to my 4 rules, what's the first step? Was always step number 1. Yeah, you're gonna find the electrons and add them all. So how many valence electrons does xenon have? You look on your periodic table, 8. And fluorine is gonna have 7. So 7 times 4 is 28, plus 8 is how many electrons? How many electrons we thinking? Almost. So, yeah, almost. So 7 times 4 is 28. So 28 plus 8 is how much? $36, like the ACT score. 36. So our next step is to look at our electronegativity to determine what our central atom is. And if you all remember, fluorine is the most electronegative atom you can have ever on the periodic table. So xenon is going to go in the middle, so central atom, and then it's surrounded by 4 fluorines, like so. So we have 36 electrons total. Now we're going to draw a bond from each of our xenons to our fluorine. So boom, 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 boom. So that's 8 electrons total. And then 36 minus 8, that's 28 electrons. Now, we need to make sure all our atoms have our octet. So we're gonna put all of our, what's it called? Our lone pairs around our surrounding atoms. So I'm just gonna go fill these up until they get to 8. So 6 from the 3 lone pairs that we added for fluorine, plus the bond that's 8 electrons. So we're gonna do the same thing to each of these. So how many electrons did we add by doing that? So I added 6 here, 6 here, 6 here. So four sets of 6. How many is that? 6, 6. Another 6, another 6, 24. So 28 minus 24 is 4 electrons. Where do our last remaining 4 electrons go? Where do they go indeed?
According to Rish's rules.
So let's add a little amendment. Oh, it was specified. Draw remaining electrons in lone pairs on surrounding atoms / the central atom. But let's add a little amendment, shall we? So keep going until you get negative. Then we'll call this 4-A for Rish's rules. If electrons are still positive, or I should say, if remaining electrons are still positive, add them in the form of lone pairs, lone pairs to central atom. So since here we have 4 electrons remaining and our fluorines are completely filled with all their octets, you can go ahead and add 2 lone pairs here to take care of your 4 electrons. So that's 2 lone pairs right here. 4 minus 4, 0. Now you're probably wondering, Rish, is that 2, 4, 6, 12 electrons on a xenon? Are you not allowed to do that? Are you allowed to do that? I have 12 electrons here. Is that valid? Why is it valid? Yeah, that's a short answer of it. So basically, if you look on your periodic table, xenon is one of those elements with a D subshell, so it can hold a lot of electrons. So because of that, xenon can have more than 8 electrons. It has what is called an expanded octet. An expanded octet. So now that the amendments to Rish's rules have been made, xenon tetrafluoride. Do you all have any questions on that? How I got to the structure that I got to? How I achieved that structure?
Would it have been okay if you put a double bond between them, between the xenon and fluorine rich?
So Daniel quickly wants to see rule 4A again. So rule 4A says if the remaining electrons are still positive, so if they're greater than 0, add them in the form of lone pairs to your central atom. So that's what we did right here. So 4 electrons were remaining when we added all of our lone pairs to surrounding atoms. So what I did was I just slapped them in the form of lone pairs on our xenon. And to answer Dylan's question, if there was a double bond on this xenon right here, let's draw that out. Let's see what happens. So there's a double bond. Notice how many electrons fluorine has. 2, 4, 6, 8, 10. And does fluorine have a D subshell? Or better yet, can fluorine have an expanded octet?
Remember, everything that can have an expanded octet is something that has a D subshell, and that starts on period 3. So if period 3 and below is able to have an expanded octet. Fluorine is in period 2, so therefore it can't have an expanded octet. So 10 electrons would be that fluorine is probably crying right now. So let's give that back to the xenon. And Susanna, I think Susanna had a question. Wow, we have 53 chats today. Pretty active group of people we have today. Susanna said, can all noble gases have an expanded octet?
Remember, krypton and xenon are the only noble gases that can bond at all. So those are the only ones that can really even have expanded octets. Stuff like helium and like neon, those can't even form bonds. So xenon and krypton are special in that they can actually form. Radon probably can as well, but y'all won't see that those go with spots.
All good in the chemistry hood? Great, okay. Next question.
All right.
Is there a question y'all would like us to do? Like maybe a molecule that looks kind of complex?
Yeah, any of these are fair game. We can do anything.
If you can, yeah. If you're not straining your eyes. The hardest one, well, which one do you think is Ariana, which one do you think is the most difficult one?
Like, which one do you see right now and go, I don't want that on the test at all? Which one just looks confusing? All right, Kennedy said M. Are there any other votes for M?
Ariana
Right.
said, go for it.
All in favor, all opposed, all right. Option M, letter M. So if we do letter M, COF2, our first step, as with anything, is to identify our valence electrons and atom number. So carbon has 4 valence electrons, oxygen has 6 valence electrons, and fluorine has 7 valence electrons, but there's 2 of them, so that's 14. So that's 14 plus 6 plus 4. So that's 14 plus 6 is 20. 20 plus 4 is 24 electrons total. And there is also no shame in using a calculator. If you need to do the quick math in your head, you are not in your head, and you're allowed a calculator on the test, so might as well use it.
Exactly.
Dr. Armand, I just have to figure out too.
Well, on the
Well,
test, you will, maybe, hopefully.
Probably. I mean, he asked you, if you're given like energy of a photon, probably you got it.
Yeah, so that's that, but I know sometimes I have to make sure that 5 plus 2 is still 7, just to make sure. So it's totally okay if you use it.
Yeah, so we'll draw out our central atom. So as Dylan said, 99% of the time, if you have a carbon, it's gonna be your central atom, because carbon likes to form 4 bonds. And yeah, there's a whole year of chemistry dedicated to that concept. So yeah. C O F F. Now, some of you all might be asking, Rish, why are you drawing it in that triangle formation? What does that triangle mean? And the answer is, you'll get to that when you learn about geometry. Or when you learn about molecular geometry, and we're gonna go over that later, probably like a week, like in a week or so from now, you will realize why I drew it that way, and why that's actually the correct way to draw it. All right, fluorine here. So once again, following my rules, we're gonna draw bonds from our central atom to our surrounding atom. So 24 minus 6, that's 18 electrons. Now, what's our next step? We've counted up our valence electrons, we have identified our central atom and surrounding atoms, and we've drawn bonds from our central atom to our surrounding atom. What is our next step? One crucial step. Yeah, so we're gonna draw out our lone pairs to our surrounding atoms. So 1, 2, 3, 4, 5, 6, and we're doing this until we get to 8 electrons. I wasn't clear on that. 2, 3, 4, 5, 6. So that's 18 electrons that we just did. 18 minus 18 is 0. But wait, carbon doesn't have a full octet. And stuff is bad when carbon doesn't have a full octet. Like there's a whole section of organic chemistry dedicated to what happens when carbon doesn't have a full octet.
It is true.
So we're gonna add 2 electrons here, a lone pair, if you will, 2 electrons to make sure carbon has a full octet. So that means we need 2 more electrons. So it's 0, so 0 minus 2 is -2. So we're deficient 2 electrons. Now, what did I say happens when you go negative? You add some double bonds to your molecule. So where do we add our double bonds? To the fluorine or the oxygen? All right, we have 1 vote for oxygen. Anybody else agree or disagree? All right, Daniel says oxygen, and Ariana says oxygen as well. And y'all are correct, it is oxygen. But why though? Why is it the oxygen and not the fluorine? Yeah, fluorine's like hydrogen, with the exception that fluorine actually wants 8 electrons and hydrogen wants 2. So halogens basically like to form 1 bond as well. And if they form 2 bonds, that stuff happens.
There, okay.
Actually,
There actually is. It's chapter 16, electrophilic aromatic substitution. So, yeah. All right, point being, if you add a double bond to a fluorine, then bad stuff happens. So we're gonna add it to our oxygen. So right here, we'll just take off this lone pair and then add a double bond like so. Now, let's make sure we have all of our electrons in the right place. So around our fluorine, we have 6, 8, or let me use this. 6 for the 3 lone pairs, 8, 10, 12, 14, 16, 6, 8, 10, 12, 14, 16, 18, 20 for our 2 double bond, or our double bond, sorry. 22, and then 24. And as you all can see, we started off with 24 electrons. So this is indeed the Lewis structure for COF2.
Yeah, and if it wasn't clear, halogens like chlorine, bromine, iodine, fluorine only like to form 1 bond. And believe it or not, I think we already said it, but there's a whole section of organic chemistry to when fluorine, bromine, fluorine form multiple bonds, because they are very reactive species. And yeah, sorry, I just had to add that in there. Anyways, carry on. So.
Yeah, so while we're on this subject, nitrogen generally likes to form 3 bonds. Oxygen generally likes to form 2 bonds. And as we've stated, carbon generally likes to form 4 bonds. Anything else on, oh wait, hydrogen, 1 bond. And I should probably add as well, no lone pairs.
Oh yeah, definitely no lone pairs. There's actually a whole section.
I mean, not in the formal sense, there isn't a formal section dedicated to that. But yeah. Anything else I'm missing? I mean, besides those, but we'll get to those at a later date. I'm talking, of course, about electron deficient atoms, but we'll cross that bridge when we get to it.
Yeah.
Now, y'all probably wonder, Rish, how did you determine that you needed 2 lone pairs on XeF4? Well, that's the full worked out solution. Are y'all ready for the shortcut? Y'all ready for the shortcut? All right. XeF4. Here's how this is a shortcut, by the way, to determine the number of lone pairs on your central atom. So you're going to take first of all, you're going to find your total valence electrons, which is what we did. We said 36 valence electrons. Then what you're going to do is you're going to take the terminal atoms and multiply them by 8. So 4 times 8 is what? 32. So 4 times 8 is 32. And then you're gonna take 32 and subtract it from your total valence electron. So 36 minus 32 is 4. But remember, how many electrons are in lone pairs?
Around the central atom.
It's a lone pair. So how many electrons? Like a pair of socks. How many socks are in a pair of socks? Two. So 2 lone, or yeah, so you divide it by 2. So there's 2 lone pairs on the central atom. And that's sort of a shortcut.
If you're in Dr. Armand's class, he's probably gonna ask you something like this on a quiz.
Yeah, he will legitimately ask you how many lone pairs are on the central atom in XEF4.
Yeah, it might actually be XEF4. So if you attended this session and you remember that there's two lone pairs on the central atom in xenon tetrafluoride, then you don't even have to do all the math, just slap in 2. And that goes for even if the fluorine was exchanged for chlorine, bromine, or iodine, because they each bring 7 valence electrons to the table. So if you drew out xenon tetrachloride or bromide, they would all have 2 lone pairs on the central atom, xenon.
So to recap, what I did was I found the total number of valence electrons, which is 36. Then I took the number of surrounding atoms, multiplied it by 8, and then subtracted that number from the total number of valence electrons, and then divided it by 2 to get the amount of lone pairs. So let's try something like this. SCl6. How many lone pairs are on the central atom in that? So how many valence electrons does SCl6 have in total? SCl6. How many electrons are there?
Yeah,
46. So 7 times 6 is 42. Plus 6 for sulfur. So it's not 42, 48. Yeah, 42 plus 6. Yeah, 48. So then now you take your central atom, or your surrounding atom, which is 6, and you multiply it by 8. So 6 times 8 is 48. Then you subtract that number from your total number of valence electrons. So 48 minus 48, congratulations, 0 lone pairs on your central atom. So yeah, that's a little shortcut if y'all were indeed ready for it. And don't worry, we're gonna go over the shortcut again at a later time as well. Plenty more Lewis structure practice where this came from. All right, so we're about to finish up here. So is there any more questions over anything we've sort of covered today?
No, we're all good. Do y'all for our next session tomorrow, what would y'all like to go over? If you can make it, it's at 2:30 tomorrow.
In room SCB 3.146.
Our YouTube channel has always been posted to. Anything? Nothing. Oh, a few more problems like xenon. Okay,
All right, that can be arranged. We can do more Lewis structure type problems.
yeah, and we eventually have is the Kahoot strictly for just Lewis structures, or is it like also like all the geometries? I think it's geometries,
I
right?
think it's both. There might be some hybridization on that too.
Yeah, okay, so eventually we do have a Kahoot that is geared towards all this stuff that you're gonna be learning for exam 3. So, I mean, it's kind of fun because it has great questions that are like the questions you'll see on the exam and you can just solve them. And I know a lot of y'all are competitive people, so yeah, there's no prize, but bragging rights that you won. Anyways, yeah. So if there's no questions. And we said more stuff like XEL, XEF4. We'll make sure to do stuff like that tomorrow. And hopefully we see you there. I'm just talking and talking. Y'all are free to go. Have a good one, Daniel. See ya. Oh, is John here?
Jonathan?
Oh, I believe it was John was here.
Oh, wait, no.
It's just me and you in there now. If he was here, he left immediately.